Let's start with the second part of the lecture on machine and assembly languages. We will look at the hack machine language instructions now. Okay, so to summarize, we design a machine language for the hack computer. We know that this computer has a data memory of 16-bit registers, an instruction memory of 16-bit registers. Therefore, and an arithmetic unit that has a 16-bit input. It means that instructions will be 16 bits, and we will use addresses of 15 bits. Memory operation will need 2 instructions. That's why we called our machine as a half address machine. So we define A instructions that will give the address or data actually, and C instructions for computation. So A instructions addressing. A instructions in the assembly language will look like this: at value. Okay, and the instruction will feed the value into the A register. In machine language, the instruction will be 16 bits. The most significant bit has to be 0. This shows that this is an A instruction, and address or data follows. Okay, so the value after that is either a number or a symbol referring to some number. How can we use these A instructions? We will use it to store a value in a register, specifically in the A register. At 17 means that we load value 17 into the A register, and then in the next C instruction, for example, we can copy this value to the D register. We can use A instruction to select a RAM location. Okay, again at 17 means we load 17 into the A register, and through the virtual M register it means that we take the value of the RAM at address 17. Okay, so if this A instruction is followed by a C instruction like D equal to M, it means that the content of the RAM location at address 17 will be copied to the D register. Okay, similarly we can select a ROM location. Right, this is our last example where the next C instruction will instruct the code to actually jump to instruction at address 17 in the ROM. The C instruction is used for computations. We denote the C instruction by 1 in the most significant bit. The instruction needs to answer the followings: what to compute, including the ALU operation and the data source, where to store the result, and where to continue the program. Okay, so this is the general syntax of a C instruction. Destination is equal to the result of a computation, and an optional jump. We may skip the jump if the program has to continue with the next instruction anyway. We may also skip the destination if the result of the computation does not need to be stored, but only used to decide whether a jump is needed or not. Okay, so in detail, the binary instruction will look like this. It starts with the 1, and then the next 2 bits are not used. Bits A and the C bits define what to compute. The D bits define what the destination will be, and the J bits define whether to jump or not. Okay, so here an example. Here we have an assembly instruction D equal to D minus A. That is, the result of operation D minus A should be stored in register D. Okay, so the binary instruction starts with 3 ones, and then the next bits identify that this is a D minus A computation. Then 3 bits identify that the destination is D, and finally the last zeros define that the program doesn't need to jump. So as you remember, the HackALU has a fixed set of operations, right? We programmed them in the previous projects. It can add, it can subtract, it can add +1, etc., etc. Actually, altogether 28 instructions are defined. In the C instruction, we have 7 bits to represent these instructions. Okay, it means that we can have a simple chip design. We don't need to code all the possible outcomes of the 7 bits. And we will define our instructions in a way that they can be easily interfaced with the arithmetic unit. Let's see the different fields one by one. The computation bits will be defined in a way that they resemble the control of the arithmetic unit. This first bit A will define the input. Okay, specifically whether we consider the A register, look at these examples here, or the memory location represented by the A register. The C bits will define the computation itself, okay, assuming that the other operand is actually the D register. Okay, and if you compare these tables, then you see that these C bits actually represent one by one the inputs of the arithmetic unit. Okay, so for example, x minus epsilon in the arithmetic unit had inputs 0, 1, 0, 0, 1, 1, and D minus A, alternatively D minus M, needs in the C instruction C bits as 0, 1, 0, 0, etc. Right? So the same bits. This will help us actually to define a simple control of our arithmetic unit. The instruction destinations, here we have 3 bits, and these 3 bits will define possible destinations to store the result of the computation and combinations of those. Okay, and again you can see that it is very well organized. D1, D2, D3 defines the possible destinations, starting from D3 it will be storing the result in the memory at address stored in the A register. D2 will be storing the result in the D register. D1 is storing the result in the A register. If many of these bits are set to 1, then the result will be saved at all of these locations. Finally, the jump part of the instruction, represented by the J bits in the C instruction. They will tell whether the program should jump to another instruction or continue from the following one. In any case, the jump is conditioned to the result of the computation, and the result of the computation is compared to 0. Okay, so if the jump instruction is jump if greater, then jump will happen if the outcome of the computation is larger than 0. Okay, etc., etc. We have simple jump if a jump has to be done in any case without condition. Again, note that the C instruction doesn't tell where to jump. So before such an instruction, the A register has to set to the address where the program has to continue from. Let's see finally a small example of A and C instructions. Let's look at a simple example given in pseudocode. If the value at memory location 3 is equal to 5, then continue the program from address 100, otherwise continue the program from address 200. Okay, let's see how it looks like in assembly language. First we have to get the content of the memory location 3. So we put 3 into the A register and then save the value of the virtual memory register at 3 to the D register. Then we need to compare this value to 5. Again, we store 5 into the A register, and then we have to compare the content of the D register and the A register. Okay, we can do that, for example, by subtracting the two of them. Okay, then basically we prepared the condition for the jump instruction. So we need 2 branches, and you will see the 2 branches here and here. So first we load the first possible ROM address, and then we give the instruction that if the content of the D register is equal to 0, then go to 100, and then we give the address of the other kind of jump and make the jump anyway. Okay, so note in this small code that A instructions and C instructions come alternately. This ends the second part of the video on machine and assembly languages.